mindset of if the math method homework doesn't get done, it doesn't get done. I sat down to try and work on it, and I was just like, mentally just couldn't do it. The killer thing about how much time the quantum exam took was that like
I spent probably 2 times that it takes to do that exam, just because I just.
Literally, like, to transfer my work, that took over, like, I had unabated 2 hours straight to work on it, and I was like halfway through, and then I did like half and half where I was doing something else and I was working on it and like in the off time or whatever. But like seriously, it took me
Just
like
feel it.
yeah. It took me like 4 or 5 hours.
It's
ridiculous.
I wrote a little book.
Yeah, for real. Yeah.
Just to transfer it?
Just to transfer it over, and then even then I was like, I'm not gonna like.
I've spent probably. I spent 4 hours each day, so really close to 16 hours when just keep on rewriting it, and like, you know, every time I worked on number 3, I was doing something just stupid. I calculated the matrix wrong, and well, GG, you know your eigenvalues.
Well, here's one big thing that like that I knew from working at St. Jude was that a diagonal matrix, the eigenvalues
Yeah.
are just the items on the diagonal.
Yep.
And like I kind of half acted like I was doing math for most of it.
Yeah.
Where like, you know, the formula is this, and then it pops out to be that, woohoo. And then literally on like the last one, I was so tired. I just said, because of diagonality, I know it's this. Moving on, and I was like, okay.
Yeah.
And then also, for any diagonal matrix, the eigenvectors are the 1, 0, 1, 0, 1, 0.
Yeah. Yeah, no, that's what I did.
I can't wait to get solid B on my soul. Also, they need to have that office, or at least a stapler somewhere we can access. Because I don't have a stapler at home. Oh, you have a stapler? Literally, the math methods, the studying for the math methods exam and doing the quantum exam has like actually injured my body. The amount of writing that I had to do.
Yeah.
Why you see me with my armband and stuff.
What a mess. It's like I'm confident on like 1, 2, 4, half a 3, half a 5. You know.
I'm confident on everything except for the turn this into a matrix, and I'm like, the cat goes, this one's supposed to be, it's supposed to be. So essentially what I did is I solved it both ways, and I was like, this answer looks stupid. All right, it must be this one. And I just went with that one. That's literally what I did. Was I started doing the algebra, and I was like, this algebra looks dumb. This algebra looks like something they'd put on a test. I'm gonna go with this one, and that's why I chose the matrix one that I did. The amount of time that I treat tests as like a game. Like I've always been being a good test taker like runs in my family. My grandfather, who I take a lot after, he one time just like pissed off my mom. He told her I'm a really good test taker. She's like, okay, fine. She had a take home test for something, and he took it with her, and she got like an 80 or a 90 on it, and he got a like 60 or a 70 on it. He's like, I know how to take tests.
Did you say he majored in computer science, or?
My grandfather knows he was a doctor.
Oh yeah, that's.
my brother.
Yeah. He's a physicist.
Well, he got his PhD in computational quantum physics, and then he was like, man,
Here's
no
a
one
little
wants to
book.
hire for this.
Thank you. Yes.
Yeah, I tried to do the thing to transfer it over to like,
Now
computer.
this time you do the hand.
I couldn't. It was just too much to type out.
Yeah.
So, if there's any problem on it that you can't read or something like that, let me know.
Okay. Okay.
I
You
try
mean
my-
the oh here, right?
Yeah, it's all there.
Okay.
I tried my best to make it as legible as possible.
That's clear. Yeah. I mean yeah.
I also did the thing where I did all my scratch work on one
Uh-huh.
sheet and then came back and did it with no scratch, just
Uh-huh.
point by point.
Okay.
Yeah, mine's a mess.
Yeah.
Well,
Lot of hard work. Yes.
yeah, no, do not show me any mercy because I don't. because I kept on like going back, making simple mistakes and
Uh-huh.
spending hours rewriting it. And,
Yeah. That is.
Yeah. So
Yeah, for the
Excessive.
for like the first half of it or something like that, I was, showing most of my work of being like, here's what the eigenvalue formula should be, and on the last one I was like, look, I know a diagonal matrix has the eigenvalues of this and this, and I know what a
Kind of
diagonal
hate it,
matrix.
right?
I was like, if you don't accept this, then shoot me.
it's like it's so tedious. Oh, yeah.
Yeah. Also, like, it really does feel like so much time was spent doing something that, if I can speak candidly, is not valuable these days. Because, at my last job, what I did was eigenvalue decompositions like significant amount of the time. But if I ever went to my boss and was like, yeah, I spent 6 hours doing that by hand, fired. Instantly fired. There was never any reason to like do
Thank
eigenvalue
you.
decomposition by hand.
Oh, by the way, did you log into our department website? I couldn't log in. Can you now from your laptop?
Sure. I
Did
can, you mean Blackboard or the department?
No, just department website.
I'm not
It
sure.
says there's something wrong or privacy
How
something.
thick is yours?
It is 11 pages.
Okay.
Same.
You
So
can log in.
what's the department website? It's
Just our department
A
physics.
hefty 10 pounds.
Physics.
I don't know how long mine is, but if you gave me an extra 3 hours, I could make it stop a bullet.
You see, that is the same thing.
Oh, you all just have an updated your security certificate. It's nothing really malicious. There's just something you have to do to update your security
How to
certificate.
do that?
It's the IT should handle that.
Okay.
So you can open a ticket with IT.
But other department website, everything is okay. Just our department to make
Yeah,
security,
well, website certificates are only valid for websites.
physics,
So.
security.
Probably something Lutz would have to do, I guess. Because he normally does all the IT stuff.
Well, really, I told the police that you made us do eigenvalues by hand, and they just banned you. Is what they did. They said that's not allowed.
Oh. How was your all's break?
Funny word.
You had a
Break.
You had a break.
Yeah. Yeah.
Sorry.
No.
They have it worse because they have you for 2 classes.
Yeah.
Yeah.
You have two. He has two. You are also. You have another.
Just the one.
Just
no,
one,
we
right?
just had yours
So he's
over
better
break.
than him.
No, I had another class that did our midterm project, which
Uh-huh.
this project actually was mathematically impossible to do in time because I was like, hey, I've got a really powerful computer, and this is for this section alone is taking 14 hours of compute time. I don't think we can do this before it's supposed to be turned in. And he came back and was like, yeah, that's my bad. I'll leave it till next week. But I was literally like sitting there.
bad.
I was literally sitting there and I've got photos of it, but like I just pressed enter and then my GPU was at 100% usage for like 8 hours straight. I pressed it, went to bed, woke up, showered, ate breakfast, and while eating breakfast it was like done. And I was like, oh, that's convenient.
No.
Do you enjoy that class?
How thick
You
is
can
yours?
say
Safe?
I hate it, but yes. I
Oh
love
yeah,
that
it looks
class.
like mine. Mine's all stapled five different ways.
Jacob, you stapled the 2 pages together so she doesn't read that part.
Well, yeah. What publisher did y'all go with to make your?
Just don't read
exams?
any of it.
Natural science.
I can show you all the scratch paper that.
Now I can stay up all night doing StatMech homework tomorrow.
No. I'm gonna tell him. Not doing it. Quit. Every time I come into this quantum class, I just say that so that way Jacob can encourage me.
Yeah. I don't know. I don't know. I think I had a stack of 200 like like blank, pages for like copy paper.
Oh.
And that's almost depleted.
On that note, Zane, could you?
Here's all my scratch work.
Could I get my God, words. They're hard.
I'll show you this.
Could I get stat deck notes from Thursday from you?
Yeah.
I had a
I'll give them to you either way.
yeah.
I think this is all three.
Oh,
That I redid
My
twice.
aunt having an emergency that once I got to the house was not actually an emergency at all.
It happens.
I'm like, so that's a participation point off my score. Thanks, Amy.
I needed every single point that I could get. Because I'm only allowed to stay 3 hours and not 7 for the exams.
She officially doesn't talk to me anymore unless it's to ask for Limburger cheese, because apparently she wants some, and I haven't been to the store to buy hers.
we're
So
talking
literally
about a professor?
My aunt.
Okay, thank God.
Yeah, no, she'll literally just message me at like a random point and say absolutely nothing but Limburger cheese, question mark, and I'm like, I was up till 4 a.m. working on my final. I'm not worried about your cheese right now.
What's so good about this cheese?
I have never known her to eat it in my entire life.
So I think the exam might have killed some of our classmates because
I'm just a chauffeur, and I used to be.
we've all got the 1,000-yard stare.
That squeaking won't get annoying over the next hour and 15 minutes.
Oh,
Who wants to slam my head in that window?
Yeah.
You'll develop selective hearing. Just like everything else.
I'm gonna walk outside and get into my car. It's just gonna still be ringing. The ringing is just never gonna stop. Go to
anyone
bed
else-
at night.
Did anyone else dream about solving eigenvalues?
Oh no.
No, I didn't sleep enough for that.
Doctor, you like that one?
Copy or print or save your image and give me what you dream.
I'm never gonna forget.
That is my goal. Let it keep in your mind.
Yeah.
Oh.
I don't
Okay,
know.
I'm just summarize a little bit, so let me keep continue.
Oh, let's go.
I know Joke woke up from a dream and was like, that's the problem, and like woke up and went.
I went to bed last night when I had an imaginary component to my expectation value. And I was like, I don't have the energy to figure out why. I'm going to bed. I've broken physics and I am done.
Well, in my transfer over from my scratch work to my final result, I was doing it, and then I caught myself saying in one breath, "No, they don't commute, but they're compatible." And I was like, "Not correct," and I went back and found my errors. It was just like, "Oh no, I'm brain dead."
Yeah.
I should have turned on my scrap work. I probably would get more points.
Just smoke screen, like, go ahead, find the part that's wrong.
Did anybody else show up to the PLC this morning to take over for you?
I was talking about angular. I was explaining angular momentum like 9 different ways. Stupid figure skater.
We had one person show up to the PLC, like one of the only people Jacob and I have seen all semester. And I'm like, I have to go. I have a meeting with Zane.
Yeah. I was like,
And I'm like, where's the
"Bye."
next person? Has the next person shown up? Did the next person ever show up? Or was Jacob just there forever with this figure skater problem?
I was there an hour and a half.
And the next person for the PLC never showed?
Oh no, she showed up, but
Oh, okay.
yeah, no. I just resumed my role. I feel like it'll be much harder to pass it on to her and to explain what I
Yeah.
just.
I was just like,
Sorry.
To go meet the boss.
have to go meet the boss. He's a slave driver.
Oh no. Wrong.
Okay, I think that is what we have.
Let me take a
And
picture of this.
before the break, sorry.
That's
So, okay, so we are trying to explain or what is the physical implication of the postulate 3 and 4. That is related to the measurement in quantum mechanics. First, we know that measurement will disperse the system, right, from state psi to state prime. That is the first issue when we measure. So second one, we interpret postulate 3 and 4 is how to determine the outcome. So to determine outcome from the measurement, as we know, because change states, right? But according to postulate 3 and 4, those new states be one of the eigenstates of system. Eigenstates of operator A, and the variable A must be one of the eigenvalue or of this A, right? So that is measurable values be among this one, and states be go to one of them. That is according to the postulate. Then the question is, this is very interesting. We want to know what the states here, what kind of value give us. But this change, right? So that is outcome. Then for unknown states, what the quantum mechanics can give is probability. Since among them, what is probability to get one of these values? So that is the probability we define here, and depend on the discrete basis or continuous basis. We have two formulas, right? So that is the issue that how to predict or give the outcome, or how to determine the outcome, or how to read the other outcome, the information, give us about the information about these initial states. And no, that is very interesting, right? But of course, we cannot have any, since the state change, so what we have just probability. The next one is, okay, the probability that depend on distribution. Different eigenvalue have the probability is different. I think, okay. If you look here, something like this, P as function A, this A, so that is expectation value A, right? So that's the distribution. Each value gives us, for given A value, this probability is where it's high or low. Then we are interested in the expectation value. That depends on state, right? That is initial state. So now, okay, we know the probability. Then let's see what is the expectation value outcome for these given states, right? So we are going to calculate this one, and this depends on different basis, continue or discrete basis and continuous basis. Then go to next. So now we are going to see if we measure A first, B second, or B first, A second, like the problem 3, right? What will happen? Are they equal or not? So that is come from another question. If A, B commute, so then it does not depend on order. You can measure A first, B second, or B first, A second, it will give the same thing. That is the first conclusion if they commute. Then, because it commutes, it can form this complete size of this commutating operator. That is eigenvector for given eigenvalue of A and eigenvalue B, we have one given eigenvector. So we have a set, right, for given n value and m value. That is the last problem, right? Then here, for the common, for the CSCO, so operator A applied to this state to give us eigenvalue A, same state, right? This eigenvalue problem. Same thing for B, it will give us B eigenvalue. Then this states B complete and orthogonal, right? So that is double check this. If you use operator. Okay. This is for the commute. If not commute, we also discuss. If not commute, this measuring depends on order. Which one first, which one second, right? So now the next question or next topic we are going to discuss or finish this discussion about this postulate 3 and 4 is the measurement and uncertainty. So now we know only have the probability measurement and uncertainty. This is we are going to discuss today to finish this topic, and then we go further.
I do have a question.
Yes,
Does the fact that all observables have to be eigenvalues of stable eigenstates?
that is according to positive 3.
Yes, does that imply that those physical aspects do not exist unless they're in that state? So the original psi has no momentum, has no position, because you did not need the operator to get the measurement?
Yeah, it depends on this one. If you measure energy, that is energy here. If you measure moment, it's moment here.
Right, but basically that.
Before you
the
do not
active-
know, yes.
The active, that you do not know, does
No.
not exist.
We
Because-
do not know exist or probability. You have to look this probability or expectation value. This is initial state. We do not know what is the energy, momentum, or whatever. So you do the expectation value, and you can see that value give you energy is close to this. I mean, the expectation value is given the peak, right? If peak narrow, that is my next discussion. That this is the fluctuation, right?
So before measurement, the position is a linear combination of eigenvalues?
Eigenvectors. So okay, here I think this one here I didn't where C come from, right? So now, I mean, okay, just space. I just insert here. So now any states, initial states, I can explain a linear combination of okay, right? You can always do this.
Yes.
So that means that is the coefficient here. How for given state, this coefficient may be big, may be small. If it's small, that probability is low. If high, the probability. But this is summation, so we do not know how much. And then that is give us expectation value. Look the statistic outcome. That makes sense? Okay. So now. And for this one, since we know that is give us the probability and distribution, so now we are interested in how the uncertainty relate to the measurement. And if you remember in chapter 2, we already discussed this uncertainty principle, general uncertainty principle. Always larger than equal to half of absolute value of this expectation value of commutator. Remember this one. So now we are going to discuss, I just extend the discussion about this. First, remember what's the definition of this? This also the ask you to do the exercises in this midterm exam, right? B. So, and if you let me just do the figure again here. So, this is expectation value. This is a square, expectation value of square, right? So here, if we have a probability distribution as for giving just a value, then if this one, okay, let me first. This product is proportional to the fluctuation, right? And this one, the peak is expectation value. So this either A or B, right? So B is same thing. I'm not sure this distribution peak maybe not the same, but let's see. So this distribution really depends on states, the initial states. If I change the states, it may be very sharp. Positions be same position anyway. Here. This is divide B prime. If they are maybe expectation value may be changed position. I just give you some idea. So where is my okay here? So this strongly depend on the states. Different states distribution different, right? So because you can see that the probability here, where is probability this depend on this, right? The coefficient here or this. So that gives us the right-hand side, this part. This part is, if we measure the states, give us initial states, how much the fluctuation or uncertainty can give in, we calculate by this. Yes.
So is expectation value defined for an operator alone without a accompanying state?
You mean this one?
Yeah, is that defined in any way in general for any sign?
Yeah, for
that is
any-
feasible?
For here, right, this is definition, right? So you want to measure whatever is energy, a Hamiltonian or a momentum or angular momentum. This psi is given states, depending on which states. Your states initial, maybe just eigenstates of the A, then your probability is 1, right? If not, linear combination or something. So that really depends on states. So that fluctuation, as I mentioned here, depends on states. Maybe the fluctuation larger or fluctuation small. That's different. So that is different. Now we look at this term. This gave us, it's always larger or equal to this one, right? So we are going to understand this. Okay. These are there's uncertainty, right? So these uncertainties come from the interference of the measurement, right? Interference of measurement. Because here, right? So when we measure, it will interference change to another state. And these states, which we go to one of the eigenstates of this operator, A, then the question is how, this distribution, right? So that distribution comes here. So that is the interference. We measure this curve system, and then when we get this outcome is probability analysis. So we have to, that is uncertainty, or that is something great to the uncertainty. Okay, now let's discuss this one. This means give a, what is, here. This give a lower limit, right? So you have always equal or larger than this one. When it is equal, when it's large. That is depend on, as I said, depend on states. So now let's discuss this case. The first case, if they commute. Then this one is 0, right? So 0 means what? The fluctuation or uncertainty of this product have this. And in which case 0? Which case are larger than 0? Which case can be 0? Eigenstates, right? Mm-hmm. So if 0, let me see this way, equal to 0 if the initial is eigenstates of joint eigenstates or the CSCO, right? So because they commute. So they have a joint eigenstates. If the initial state is just the eigenstates, then you know the probability is 1 here, right? This is a 1, only one of states. So that means this equal to 0, so that means this delta A is 0, delta B is 0. So simultaneously, that is what the simultaneously measure. We can measure simultaneously. Measure simultaneously. Yes.
So that's delta A is 0 because it's an eigenvector of
Yes.
A. But is it possible to have, for example, the degenerate eigenvector? What happens if the degenerate eigenvector that's being given is only an eigenvector for one of them? Will that still be 0?
Okay, so this is the conditions here, right?
Mm-hmm.
Condition means they commute each other.
Mm-hmm.
So let's just build up this. Right? Build up this. So then we measure. So in this case, okay, I think here already, that is here. So A measured, it will not disturb system. The state still the same system, state. So the exact 100% the probability is 1, it's given this value because we know which state. In this case, we know suppose we know the states is one of the eigenstates. Same thing for B. So you see here the fluctuation, you will see that is equal to 0, right? Because this is equal to this one. Because they are eigenstates, right? So this one is A squared AN. This A squared gave us eigenvalue also AN squared, right? So that's 0. Same thing for B. So in this case, just very sharp line. Just one line, right? That is the case. But larger than 0 if it's not out of this, right? It's not eigenstates. Then must be linear combination. If we have linear combination, we have a coefficient here, the probability. So in this case, these are not 0. That means delta A will not be 0. Oh, sorry. Delta B will not be 0. I think when I say it's not, it's because this is not neither the eigenstates of A nor eigenstate of B. So your measurement for this case must be has a distribution. But this is has to be very sharp. I think since this I cannot say how sharp it is. But since this limit, lower limit is 0, so that's be maybe just 0.001, very small, compared with not commute case, right? So that is the first case. Second case, if do not commute, right? That is more general case. Okay, then definitely this one also has several cases. Maybe, let me see, let me do this way. Constant or maybe 0 by particular case, the states, or some of variables is expectation value of this one, right? So now let's discuss this one. If a constant, so in this case, the fluctuation over uncertainty of this measurable A and B together, that is always larger or equal to constant here. And when it is equal, when it is not equal, it is not like this, because we do not have a joint eigenstates. So this just gave us, this uncertainty of these two variables, when we measure the product of these two, must be larger than this one. Example is, we know the position and the linear momentum, right? H bar. So, okay, I think since we need to consider this absolute value, since here is absolute value, so we can, that is H bar, right? That's a constant. So what that means, whatever these states, this initial states is any states, but this part is a constant. So this, then what happened is this larger than this one, I mean I have half, right? Half H bar. So this product, so that means delta x, delta px, larger or equal to half of H bar. Here, it depends on state. The left-hand side depends on and how fluctuate. That's your initial states. What is away from this value or close to this value. So that is this case. This case is again we have something like this, but this does not mean we are in this eigenstates or joint eigenstates. This is just for, I think this part still depends on state. Depends on states. So here, one example is like angular momentum. If you have a spherical symmetry, we know this angular momentum do not commute each other, right? There's Lx, Ly does not come equal to Lz, right? So that commutator does not show the constant. It's be another operator. But if the states such that this, the hydrogen, the electron in this s orbital, so that's equal to 0. That particular state is equal to 0. In that state, so we measure some others. If Lx equal to 0, how about Ly, Lz? Maybe equal to 0. If a spherical symmetry, maybe larger than 0. That makes sense? But not come from here, right? This is a eigenstate. This is an arbitrary state. Okay, variable is something like, I mean, any operators, if we say C. So C is the commutator. And if this is, again, like this is another operator, but this expected value is not constant, and how much it is, this will depend on state. Therefore, this part, the given state, the product of this, should be larger than this one, or equal to this one, but this one also depends on which state. That makes sense? I think that is what the discussion or interpretation of this measurement for postulate 3 and 4. Now we are going to go to the last postulate, postulate 5, which is also very important, and we have a lot of topics we are going to discuss. Right. So what is possibility 5? It is called about time evolution. Evolution of the states. The quantum state system, right? But the state time evolution. So let's, if I repeat this, the possibilities give us this one. Time evolution of this quantum states follow the Schrödinger equation. This is a possibility 5, right? Now we are going to discuss this. What is the physical implication, or what is how to interpret this? So there are several issues. Now let me first discuss one. Is the this operator. Operator. What does it mean? So we know operator Hamiltonian, momentum, linear momentum, angular momentum, position operator. This one is another operator, right? From here. So let's see first is dimension. Which dimension? Who can tell me? Dimension of this operator. Look at this formula. Left-hand side and right-hand side is equal, right? So this side is Hamiltonian, that's be joule. Or what is energy, right? So this has to be also, right? Dimension, yeah. Same as Hamiltonian. And that also makes sense. You know that this h bar is joule second, right? So joule second, this time cancel, so that is joule. This is joule. So that's speed like this. Second, it is Hermitian. That means IH partial T letters be equal to itself. Why? Because the right-hand side is Hermitian. H we know is Hermitian, right? So the right-hand side, left-hand side is also Hermitian. And you can prove yourself. It is Hermitian. So, what is the role? The role of this operator. What is the operator act on states? What happens? What is the role? It will change the time, the state, right? In terms of time. So change the state in terms of time. So that is characterized how the state evolution with time, right? So that is number 4. Maybe we can rewrite. Let's rewrite this the Schrödinger equation. We're going to move this one to the left-hand side. T equal to, so that is minus I h hat over h bar. Okay, if we rewrite, you will see here this one, this term. Because this is the left-hand side is going to see how the partial derivative of the states with respect to time. And what happened? This one will control controls the time evolution. Evolution of states. Okay, that is the first discussion about it, or interpret this Schrödinger equation. We will focus on the new operator, so we have some of feature of this operator, the role of our operator, right? Now, second topic is time evolution operator. Okay. These questions come from here. So if we have state of t, how the states or evolution from the initial state t naught, right? Evolution. This is a question. Or the relation between these, how we enumerate the states from t naught to t. So we introduce or define. Introduce an operator. U hat t naught. That is this one. Time evolution. We introduce. So if we introduce, that means the state of t is nothing but the time evolution operator act on the state of t naught, right? That is the role of this time evolution operator. So that means the state from t naught to t is nothing but this, like the operator act on states, initial states. We know this is a operator act states. It will change new states. So in this case, this operator change states from initial t naught to the t. And the shape of the wave function still keep the same, just depend on time, just a function of time, right? That is the definition. So now we are going to introduce this one. Okay. Properties. Okay. So how about this one? From t naught to t naught. That means it does not change, right? No time evolution. So it must be equal to identity, right? The proof is very quick, very simple, right? Because if the state t naught is equal to identity, right? State self, I just multiply identity operators same. Then that is we have two, right? This is I just insert identity. Then according to the definition, so the states T naught should be the time evolution operator U from T naught to T naught, right? Doesn't change the time. So you see the both sides here, this is equal, this is equal to be equal, so that's why, right? So that is, if we, and that makes sense. No any change, right? No any time evolution. With B, if we have a time evolution from T naught to T2, that equal to like chain evolution, that is T2, T1, and then from T naught to T1. This can also very easily to prove because the states psi T2 equal to, by definition, right, equal to U T2 to T, from T1 to T2, psi T1, and then psi T1 is from T naught to T1, right? So now I keep continue, T2, T1, did I, yes, T1, T naught, sine R, T naught. So, yes. And this is like trend, and that makes sense. We just T naught, T1, intermediate step, T2, and T3, and T final, or T infinite, right? Now this time solution. Okay, now when we know this, so next one is how to determine, right? How to express this form operator, right? We know it's play the role as a time evolution. Then what is the operator looks like? What kind of a formula? So how to do this? We need two formula or in relation. First, by definition, that is by definition here. Second, according to the Schrödinger equation. Okay. So second one, according to the Schrödinger equation, the time evolution is controlled by the Hamiltonian. Okay, we are going to use these two equations. So now, let's look at this one. Since this is this, right, I'm going to substitute this one into here. This is equation 1 and 2. So substitute 1 to 2. So now let's partial, okay, inside here, U T T naught, partial T. Right? This one up here are equal to this does not depend on time, right? It's a T naught. So then the partial T is only for the operator. These are variables. So here, then from here you compare because there is something here equal to something here, right? So this and this multiply this function the same. Does not depend on time. So we immediately got this. I H bar partial U operator T T naught partial T equal to Hamiltonian. Sorry, yes. Okay, so we are going to solve this equation. Equation 3. Now to solve this one, we need a condition. If the Hamiltonian depends on time, it is complicated. But fortunately, in most cases, the Hamiltonian does not depend on time explicitly, so we can solve this. So now, just consider if the Hamiltonian does not depend on time explicitly, then here I can, so this one, you can also partial u t naught, partial t equal to, I divided the I h bar on both sides, so that is negative I Hamiltonian h bar u t naught, right? Things like this. So now, if you see here, if this does not depend on time, I can divide it like this. So I have a partial u hat t naught divided by u hat t naught. I move the t time dependent part in the right hand side, and that is minus I h or h bar partial t, right? I just divided, multiplied partial t both sides. I move this one also both sides. So I have this part is a function of u hat. This part, if does not depend on time, I just do the time integral, right? So immediately have a log u t naught, and the integral from t naught to t, that's equal to minus I h h hat or h bar t minus t naught, right? Okay, so then u t naught is equal to u t naught exponential minus I h hat or h bar t minus t naught. Now, properties. The u hat t naught is I, right? So that is equal to exponential. That is very important expression to express what is this time evolution operator. It is exponential and controlled by Hamiltonian. That is very important. Later we are going to discuss this also associated with the symmetry. So when we have this, now this is of the condition here, right? Condition, and this in most cases it is true. And you can know the property C is a continuum. So since we have formula property C, we will see that it is unitary operator. Because you can see here, right? So let me use this space. Because u dagger is exponential minus I h hat or h bar t minus t naught dagger, right? So when we do the dagger, the numbers become complex. So I minus that become I, right? So that is E. Sorry, that's inverse, right? That is not that. That's unitary. Is inverse. So that is minus become I. If you want to say it, because we know Hamiltonian is a Hermitian, right? That is E I. And you know, if I say that is inverse, because you know this one multiply itself is cancelled since Hamiltonian commute itself, right? I need to write. This is this one, right? Okay, because you see, they just cancel. This is positive, negative, they cancel each other. That is. So, and that makes sense. In chapter 2, we already learned this transformation, even though in that time we didn't say time revolution, but for all this transformation is unitary since we do not change the norm of this wave function or shape function from this to another. We just change, in this change time, right? So that is the properties, the third property. Okay. Now, this is the second topic. Now go to number 3. Keep continue. Just 3. Okay. Stationary state. What does mean stationary states? There must be time independent, right? So we call it stationary state. So now let's see here. Okay. Hamiltonian, we know that is kinetic energy plus potential energy operator, right? So if potential energy operator, it does not depend on time explicitly. That means then Hamiltonian also equal to 0, right? Because this does not depend on time, right? This is kinetic energy operator is momentum operator square over 2m, right? So we have this. And if I have this, then you can, you can see from here. So if from here, this is time independent, it does not depend on time, and this we are looking for the time evolution of space. So what happens is this space be separable. Let me use right? That's the way we know this. So if this is the case, now we are going to substitute into the Schrodinger equation here. Substitute here into here, then we have IH bar partial. Okay, I'm going to move this because this only depends on time. And then here is only the function of R equal to H, the product of a space multiplied with this function of time. So you can see here, the left-hand side, I move this time-dependent part on the left-hand side and the space-dependent part on the right-hand side, so I have so I have even, you can either use, because it's only function time, this partial you can use D, right? dt divided by ft, and then equal to h here from partial to total is because the function is only function time, right? So I just change this one. But if you don't change, it's fine, because we already separate the function, only spatial part multiplied the time part, so this is only pure time-dependent function. We do not know what this function we are going to solve it, find the solution. So you can see here, this is depend on time, depends on t. This depends on r only. So if the left-hand side and right side always equal and their variables different, then the only possible solution is they have to equal to constant, right? Otherwise, it's no way, right? Since this all this differential. So if it is constant, now we introduce constant, we introduce E. Yes.
Why are we able to multiply two kets in the separability part? See, right side.
Oh, sorry. Yes.
No, I thought we were. Isn't multiplying two kets invalid?
Let me first make this correction. Okay. You mean here?
Yes.
Yeah. That two cats is they can multiply, right? You mean we cannot do the two cats multiply each other? Your question is?
Am I misremembering that? Don't we have to do a cat and a bra and a bra and a cat? We can't do cat.
That is inner product. Yes. That is inner product is you need a bra with a cat. But the cat can also multiply another cat. Okay, maybe this way is not easy. Then if we make this as a position representation, you might, this function multiply another function, you accept. This is just like, let's consider this way, if you agree. Do you agree? state of R is vector, we have three components. So these are components x and y and z.
Okay.
Then this one is a function is two variables, r and t.
Okay.
Then I separate r and t.
Okay.
Okay.
So just to clarify,
Yeah.
whenever you're writing these kets here, it's not representing a matrix of column matrix.
No. Yes. Yes. In that case, the column matrix cannot multiply column matrix again, right? You mean that is your answer is your question. This is a not. We cannot do. Yes. But here, that's why I use here. You will see this one actually just a function, one dimension. If you use a column, I mean, most case people discard this or Schrodinger equation in the position representation. Then you can understand position representation does not use the column to represent, so that is fine. But later, I mean, let me finish this one. You can see this one just a kind of function, exponential function. So like a prefactor or phase factor, something like that. Then your wave function actually is that phase factor multiplied with ket. And that phase factor is just controlled by the time. For this case, maybe, I think maybe this case is not, this is addition, right? But you know, always we can use this notation here for, let's remember we have a delta. It's always like x max x naught, y max y naught. It's a product. Something like this. So I will not. I don't want to do this because this is also a states. Just let's say this. This states include x components, include y components, include z components. And if R, yes, that is x, I, y, j, and z, k. This vector, this states. So states just states. If you have this one, if in the position representation is function here, right? This one is f. If you use the same x, y, z is like this. That makes sense? So when we have ket, always like this, but if a vector itself is addition of the components. Okay, now let's keep continuing. So here, if we equal to, so we have two equations here, right? I h bar df I think, yeah, let's use ket again. But here, actually, this is just dt equal to e, and another is so we have two equations here. The first equation, to solve equation 1. Equation 1 is simple, right? This is a d ft divided by this log ft and the dt with this continuous. So this one is very easy. I think mathematically you accept it like this with the directory result. The solution for this is very simple. It's exponential minus I energy right, so here, we just move this dt to this side and divide the h bar both sides. We have the negative I over h bar. And this time, this right-hand side is log ft. This one is this t, and we have this. So you see, this is just like a phase factor here. Normalized is 1, right? The norm.
Dr. Yu,
Yes,
how did you go from the separation
yeah,
to the constant?
here, right?
Mm-hmm.
So this equal to this. And that means this side equal to this one equal to this.
And what makes you say that the Hamiltonian times the ket over the ket is a constant?
Okay. I know this equation only depends on time.
Mm-hmm.
That equal to the right hand side only depends on r. So if this set equal, there's no solution, only they equal to constant.
Okay.
So then I have two equations. This one equal to constant,
Mm-hmm.
that is this one, and this one equal to this one.
Because if one depends on time and the other can't.
Other depend on space.
Yeah.
So if you have two variables or function, the total is two different space, but they always equal.
Mhm.
They only equal to constant.
Okay. that
Okay,
makes
so
sense.
from one we have the solution, and from equation two we have this formula here, and but you know this one eigenvalue problem, right? Eigenvalue problem in real space. It does not depend on time. So sometimes we also call this one over time independent Schrodinger equation. Here, this is time dependent Schrodinger equation. And this is so sometimes we say, please solve the time independent Schrodinger equation. That is nothing but this one. And this chapter 2, we know that is an eigenvalue problem. Operator applied states equal to the constant applied states. So these solutions will give us eigenvalues and eigenvectors, right? So this one, only time dependent only, right? And give us how the time evolution of states, that is only from this term. And so what we have to do. Okay, so once we have this, now we are going to introduce stationary. So what is stationary state? Stationary state. The definition is if the states can be written in separate, okay. I just prefer use this one. So now we already obtained this time dependent. So here, when you write in the matrix representation, this one still column, and you just multiply this space vector to explain this ket, the ket product. Okay, so we call this stationary state Y because if you look this, the probability is equal to, okay, it's a complex conjugate, right? Et over h bar minus I over h bar t, and the inner product of, so this one is equal to 1, since they cancel each other, it's only equal to the inner product of the real space function, and that's so we call these states as stationary state. And when we state that the states can come, only condition, Hamiltonian does not depend on time explicitly. And Hamiltonian does not depend on time explicitly means the potential. Potential does not depend on time explicitly, then immediately we know the Hamiltonian does not depend on time explicitly. Okay. Now once we know that this stationary states, now we go back to how to represent or express the total states. So now we are going to express the total states. Okay. Again, condition. If the Hamiltonian does not depend on time explicitly, and we know, suppose we solve the Hamiltonian, have its eigenvalues or eigenvectors. That means if we solve this and we have the solution for this, now we can represent this any states at any time. So how to do that? The states at any time as depending on time evolution operator u, right? U hat from t naught to t, and psi states t naught, right? That is this. Then we are going to do details. So now we already have the expression of this time evolution operator is exponential minus I h hat over h bar t minus t naught, right? That is u hat. Okay. Then we are going to insert the unity operator. Here. Now this unity operator I'm going to construct by this eigenvector of Hamiltonian. So summation n, the exponential, this is u hat operator keep here, t naught, and then here this is a phi n, psi r t naught. The reason why I insert I here, now I can have this is a function of h hat, right? And we know any function of operator applied to the eigenstates of the operator is equal to the function itself, but replace the operator by its eigenvalues, right? So here, Hamiltonian, this is the eigenstates of Hamiltonian, so very easily you can have the summation n exponential minus I, so now replace h bar by en. That makes sense? Let me write down and I'm going to explain. Sorry, this is a minus t minus t naught. And here it stays still here, right? Okay, now here. This is a function of h hat, right? So a function, if you remember, I think if you have a function operator A and apply the eigenstate of A, that's give us function. It's just replace operator by its eigenvalue. Remember this? Right? So then this is a function of h. Then what happens is keep functional, but only replace h by its eigenvalues. Okay, so now I'm going to introduce, this is what? This is the initial states project to the eigenstates of Hamiltonian, right? So I'm going to say this is a coefficient Cn. So now finally, you have Cn. Now I'm going to make Cn inbound. And exponential now here, this is not operator, it's value. And linear combination of this in terms of this eigenstates of Hamiltonian. So you see here, that is the stationary state formula. This is one of the stationary state formula here, right? And here, for any states, so time evolution, then ask her to find any time, if we know the initial states, how to find this any time t, what is a wave functional or state. You just first calculate the coefficient Cn. And this Cn is nothing but this initial states project to, or inner product of initial state with the one of the eigenstates. That's the coefficient. And multiply this function, which is time-dependent function, right? Something like this. And then linear combination or extend is a superposition in terms of the eigenvector for Hamiltonian.
this relationship why things with higher energy have higher frequencies?
Say again.
Is this relationship why things with higher energies, like a photon with a higher energy, has a higher frequency? Because the oscillating term and the e to the minus I is greater, which means that it's
Yeah,
frequency higher.
This one is, this is a frequency, the oscillator here. But high energy, if you say this is energy higher, then you have a high frequency, yes, that is a control this oscillation of states. Yes, if you in terms that the oscillation with high energy, yes, that is this control that. And of the states is what the states with the states is at high energy friction states over low. It depends on this one. This is a weighting factor or like a weight, right? Weighting factor. So any states here, I expand in terms of different frequency here. But because any eigenvalue have a series eigenvalue, lower and higher, so we have a different frequency, different states. But if this coefficient is only for lower states, then that state in this low friction state. If in the high, if they dominated by the high friction state, this coefficient is bigger, like expectation value. So what states, in which states is determined by this, and this is determined by the initial states. And control all the frequency, yes, here. Okay, so we have this now. If the position representation, this is an arbitrary, right? We didn't give any representation, so in the position, very simple position representation. So left hand side just project to this basis, right? And the right hand side, Tn, this still keep it because this is the function. And this one is. Right, so this one, in general, we say wave function is this is a CAD. We are use function, right hand side. And right hand side, the right hand side, summation C, there's a coefficient, there's a factor, there's a vibration factor, and then this, now I remove the CAD bra because now it's in the position representation, function just function, or CAD is just function. Okay, now the number 4 topic we are going to discuss or interpret this positive 5 is about this conservation of probability. So now if the function is depend on time, right? How about the probability is depend on time or not? So now number 4 is the conservation of probability. And we are going to introduce probability density and probability current density, follow the ratio. It makes this particle conserved. That is, any particle cannot arbitrarily created or destroyed. So that is about this. Because we know the probability, the wave function gives a probability to find a particle, right? Okay, so now the total probability, P, right, is equal to, if we use this, the CAD, the Dirac notation, at any time, that's this inner product, right? That is the total. Or, if you use the position representation, is integral of this X function norm d. How much? Total probability means the probability to find the system somewhere in the space. Then we integral in the whole space, so that we always find always 1. So does it determine time? Should be equal to 0, right? And to prove this is also very easy. I'm using capital P, since later we're going to use a lower p as a probability density. So proof also very easy, because dp dt, p by definition, right? So that is partial de Broglie with time multiplied the cat and plus the Broglie t and do the partial. Okay. Cat. Then we are going to apply the Schrodinger equation here. So this one, we know the partial cat has this, and then we take the complex conjugate, then become bra. So this bra, this takes the minus, right? Minus h bar, h bar. And this one is a bra h hat plus the dagger, but h hat, h is Hermitian. Okay, so now this part is this part. So I have divided h bar both sides. Then if we before take this complex conjugate, that is minus 1 over h bar. So when I take complex conjugate bra, the minus becomes plus, right? So that is I h bar. Okay. Here, let me use this one. If you do not agree, then just remember, so because this is equal to itself, right? Hermitian. That is the first one. This part equal to this, and then multiply this. So that is first part. Second term. Second term plus now this bra I keep here. And this one is here, right? Minus I h bar h hat. So you can see they cancel, right? Since here this plus is minus, and here h hat equal to h equal to 0. So yes, this is analysis. This is the proof. Okay, so that makes sense. Means the total probabilities be always 0, since it does not depend time. The probability give us the find particle system somewhere in space, and that be always 1. So they cannot, the system cannot suddenly disappear or create outside space or whatever, increase double. So there's no such possible by conservation of particles, so that yes makes sense. Now we are going to consider the probability density. That is interesting. That is probability density is find the particle at the sum of a space r and time t, right? So now I'm going to use rho. That's the function time. That is give us is only, okay, now, in the position representation. Let's just consider. So here, the cat, and this one is a product of the function RT. It's a complex conjugate multiply itself. That is definition. So you can see this definition just function multiply itself. This one is integral in the whole space. So what does it mean? This one means to find the probability of system at the position r at time t. Right? That is this one. So now we are going to see how about this one, depend on time. Because usually it is also function position. Right? So R T, right? So we are going to see how the time revolution of this term. So in order to, okay, let me just go one step and then we can keep continue. So in order to do that, we are going to use this relation again. RH, now in the position representation, the Schrödinger equation, T is H hat, that is equation 1. Then if we take the complex conjugate, so then I becomes minus I, and here psi is psi star. Here, Hamiltonian is, we use the position representation. So instead of this position representation, Hamiltonian, the kinetic energy part is this one, right? And plus potential. Here we didn't discuss the stationary, so the potential may also depend on time. We just write down in general. But that is in position representation, equation 1. Then here, this is a real, right? So that is still keep here. But here, this is the complex conjugate. Potentials are real, right? All right, so let's keep here, and we are going to see this one next Tuesday. I think we can finish on next Tuesday the chapter 3. Then you just try to remind what we discussed in chapter 3, all this quantum mechanics, how to establish quantum mechanics theory based on 5 postulates. The 5 postulates, each one has a lot of information here, right? Even though the statement is simple, but for each one we know it includes a lot of information physically. So we try to understand all with those mind or knowledge. Then chapter 4 we are going to apply to solve the quantum system, 1 dimension, 2 dimension, or 3 dimension, right? So that is the next job. But chapter 3 just build up our basics about the quantum mechanics. Then we have the tool to apply to the different systems, how to solve. Each individual system depends on the potential, right? If you look this, the key is here, and here H is key is the potential. Since Hamiltonian is T plus V here, this one fixed. The only difference is this one. Different systems have different potential, then that makes the diversity of the world. Oh, yeah. Okay. All right. Let me see. This is yours, right?
Mm-hmm.
And this is yours. Hello. Yeah. Okay. Thank you. Good. Good. Yes, I can see how effort you did. Good.
You have enough to make another book.
Yes, another book.
You need to plant a tree as a class to apologize.
My undergraduate professor always told me, learning is not sustainable. I came into college trying to write all my questions on like a single sheet of paper. He's like, if you do not write on each question on a separate sheet of paper, you're
still
points.
not yet
And I'm like,
putting all the knowledge in your mind. When I was the master degree student, and the professor gave me the Hamiltonian, this like Ising model, right? Or Hubbard model. Try to derive the formula. I spent the notebook, several notebooks.
Mm-hmm.
And the professor said, oh my God, okay, you'll pass. So I spent time to write each equation step by step.
So if we just turn in enough paper.
Enough, but not each paper, not only one letter. Right?
Yeah.
Wait, hold on, I have some more.
We'll keep that in mind for the final.
Yeah.
Yeah. I also kind of might be, different. Since when we solve the 1 dimension, usually it's a position representation. So the matrix takes time. Position, maybe the functional. Maybe, but yeah, and the angular momentum again go to the matrix. But that may not ask you to solve the eigenvalue problem each time.
Yeah.
This is just do exercises. Build up yourself. And
So that way we have dreams about it.
Yeah.
All I know is I thought I would never finish number 3.
Oh.
I thought it was never going to end.
Question, ask one more, right?
Yeah, no, I emailed her and I was like, hey, just to be clear, you intend for us to do this? And she was like, yes. I was like, okay,
Yes,
cool.
otherwise-
What I didn't want to do is me to come back with my book and y'all be like, you know, there was like an easy shortcut that's just like 2 steps, right? That was my biggest fear.
Yeah.
But hearing us all go through it,
Otherwise, you cannot, probability you cannot answer, right?
yeah.
Yes.
Okay, thank you, Dr. Yu.
Okay, see you.
Here.
Go to